I'd like to give you guys a quick little visual show for what the determinant actually looks like when you graph all of these linear transformation matrices that we've been dealing with so often. Right now, what we're looking at, if you look up in the top left, we're looking at the matrix 1, 0, 0, 1, the two-dimensional identity matrix. And you can see what this does, and in my class at least, it was barely vaguely mentioned, is that what this is actually encoding are the positions of E1, the first basis vector, and E2, the second basis vector, which we know start off at the positions identified. I shouldn't say identified, but shown in the identity matrix. So we have our E1, which starts at 1, 0, and then E2 at 0, 1. And this matrix is just saying do nothing, keep everything the same. And what I have here is a little visualization of the determinant, which is the area spanned by these guys, spanned by the quadrilateral formed between these two. We can see that if we change things a little bit, now this matrix is saying take the first basis vector, put it at 1, 0, take the second basis vector, put it at 2, 0. And you can see the impact that this has had on the rest of space. In fact, all y coordinates have been multiplied by 2. Let's do some more tweaks. You see now we're taking all of our y coordinates, multiplying them by -2 while we're leaving our x coordinates the same, and that's giving us a negative determinant. And there's an intuition for the right-hand rule that also works for this. If we go back to our identity matrix here, here we have the first basis vector on the right of the second basis vector, and as long as that's the case, we can do anything we want to our determinant and it will be positive. But as soon as they cross sides, we are going to get a negative determinant instead. And you can see with some of these larger values in here we're saying take the first basis vector, 1, 0, and put it at -3, 1, and take the second basis vector, 0, 1, and put it at -3, 2. And then we're getting this determinant right here. Additionally, let's see, we can map the entire grid back onto things. If we go back to our, it's a little trippy. If we go back to our identity matrix, if I can find it, yeah, you can get a better sense of really what's happening to the whole of space when these kind of transformations take place. You can see all of space getting squished onto one line here, and you might, without even looking at the matrix that this forms, you might have some sort of intuition that this is what a determinant of 0 looks like, and maybe not even just because we don't see our little determinant quadrilateral anymore. But in fact, yes, this is a determinant of 0. You can see it up here as well. All of space has gone from being defined fully in 2 dimensions to only being defined in 1 dimension. And you can go numerically and think about, okay, well, we only have 1 pivot position, or our columns do not span all of our 2, so of course we're going to have a determinant of 0. Yeah, I'm not sure if there's anything else that we need to see here, other than I do like the animation of space kind of flipping back around on itself. I think it's pretty cool. But hopefully this was a little bit helpful. Yeah, there's not much else to do here. If you didn't know what a determinant looked like, maybe this helps you a little bit.